Hi all. This is going to be the lecture one, chapter one of Numerical Linear Algebra series based on the book from Professor Trepton Lloyd. So we begin with what is matrix vector multiplications. So we all know the what is matrix vector multiplications, and it results into another vector called B, and each element of a vector B, like Bi is the inner product of the particular vector x with respect to that particular row, that ith row for the Bith element of the vector B. But this notion of that inner product between that every row with respect to the vector x is what the general concept is. But in this chapter we will have a different interpretation based on the linear mapping. So what is linear mapping? Any mapping is termed to be a linear, obeying these two properties. So if matrix A is operating, it's like kind of an operate like a operation operating on the vector two vectors x plus y, then it can be based on the principle of superposition. It can be expressed as ax plus ay. Similarly, if alpha is a scalar which can be multiplied with the vector, and again it is operated by a linear operator called matrix A, then it can be expressed as a alpha times A times B. So this is termed to be as a linear mapping. So what it intuitively says is that if there is a linear map from n-dimensional space to m-dimensional space, then any that map can be expressed as a matrix multiplications of an m cross n matrix. So then coming again to a concept of matrix vector product, it can be viewed in a different way. This is very important. So this can be arranged in terms of a visual representations, that any vector is any matrix A multiplying on a vector x can be expressed as a linear combination of columns of the matrix A with the coefficient of expansion from the vector x. So this is termed that the resultant vector B is expressed as a linear combination of the columns AJ. So this is going to be a slight difference in the interpretation. The result is same, the vector B, but the equation 1.1, the way we are interpreting, and the equation 1.2, the way interpreting is a bit different. 1.1 is interpreted as like like a matrix A operating on a vector x, but 1.1 is difference gives some kind of interpretation that the vector x acts on A to produce B. It means that vector B can be expressed as a linear combination of columns of A by a coefficient of expansions from the vector x. Similarly, a matrix multiplication also can be viewed. Each column of B, like Bi, can be expressed as a linear combination of the columns of A. So for example, the jth column can be represented as a linear combination of columns k k is equal to 1 to m, with the coefficients of expansions coming from the jth column of vector C. So this is the interpretation for matrix multiplications. Similarly, the outer matrix will be like one is a column vector, one is a row vector, and that column vector into row vector gives you the matrix like m cross n matrix. This is m and this is n. Then these two vectors are multiplied to give you a m cross n matrix. Then also we need to know about the properties of the matrix. What is range of A? What is null space of A? Range of A is are the set of vectors that can be expressed as Ax or some x. It means that range of A is the subspace of the n-dimensional space spanned by the columns of A. The columns of A can be will come into a later concept like what is linear independent or some, and what is rank of a matrix in a later part of this lecture series. So the range of A is also called the column space of A. So what about the null space of A? The null space of A is a set of vectors X such a way that it satisfies this equation Ax equal to 0. So in other words, it can be expressed that when a coefficient of expansion is when the zeroth vector is expressed as a linear combination of columns of A through a coefficient of expansion of vector X, then it means that the resultant whatever the vectors which has a coefficient of expansions resulting into zeroth vector is termed to be a null space of A. Then column rank of a matrix, row rank of a matrix is termed as a dimension spanned by column space is a dimension spanned by the row space, and usually row rank equals the column rank. If we have an m cross n matrix, usually m is greater than n, then maximum number of independent uh, 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 column, because the column is less than the number of rows, then there will be a n linearly independent column. Then the rank of a matrix is n. This is what the theorem says. A matrix with m cross n, m greater than n, has full rank if and only one if it maps no two distinct vectors into the same vectors. What does it mean is, if something and we are operating on any vector coefficient of expansion, where we have a two different coefficient of expansion which resultant into a two different vector, not to the same vector. That is the concept behind this theorem 1.2. The inverse is something a property of a matrix. So it is only applicable to square matrix, and which has a full rank matrix. It means that all the columns are linearly independent. Then there exists a unique matrix called C, where the matrix of that multiplication results into an identity matrix. Since every square with full rank has an unique Z, then that Z can be termed as the way this is called as the inverse of A. It means that the A, if it has an inverse, then the matrix multiplication of A and A inverse will result into an identity matrix. So these are the other conditions. If the matrix is an invertible, then it has a full rank M, and the range of A is an m dimensional space, and the null space is a zero dimensional space, and zero is not. We'll come into the concept of eigenvalue, what is singular value, and this then determinant is not equal to 0. These all are same in one among the other if we call that A is an invertible. So what does a matrix inverse of a matrix operating on a vector B? We already know that the B is a coefficient of expansion on an invertible A inverse to give you a resultant vector. But it can be in other way that B is a vector which resultant from the coefficient of expansion of X A through the columns of A. So it can be in the another way. We can interpret this resultant will be into an X, but at the same time we can have a coefficient of expansion of X on the its original matrix A to resultant into vector B. This is what the diagrammatic representations of this. So A inverse B means there is a coefficient of, this is the coefficient of expansion of B on this one to give the resultant vector. At the same time, if you multiply with that one, then that coefficient of expansion of B will give you the it's an expansion of the identity matrix. So this is what some kind of notions we can get from the invertibility of the matrix. Here throughout the lecture series, we assume that M is greater than N, and M cross M is a square matrix. Hopefully we'll come up with the lecture 2, which is about a very important property of the numerical algebra called what is orthogonality of the vectors and what is orthogonal matrices or unitary matrices. Thank you.